maybe on their second season, they went to the firing range for cannonballs, and they shot it and bounced off like the pile of gravel, went up into a residential area, went through 2 houses, and broke the windshield. One of the family wasn't there, and the other, the grandpa, was there, and he thought it was just the real.
Wow.
Oh my God.
That's a really interesting science going on. Compare these two impacts.
So, we're going to watch a little perfect inelastic video.
This may just seem like some gratuitous violence, but there's actually some really interesting science going on when you compare these two impacts. You would think that doubling the speed would give you twice the severity of the impact, but the physics says you're actually looking at more like 4 times the severity of the impact. Our sensors are showing 3 times the G's, and our wreckage is showing about twice the damage. So what's going on here? Well, just like this can, the more I crush it, the more it resists crushing. There's some complex physics going on here, but you don't have to be a rocket scientist to understand it. The cars speak for themselves.
They certainly do. After 2 spectacular crashes, they have their benchmarks for car carnage.
Well, we've got our data points.
And they are lovely. I guess it's time to move on to the main event.
Yep.
This car right here hit a wall at 50 miles an hour. This car hit a wall at 100 miles an hour. I think the difference is pretty clear. The question is, when we smack 2 cars together at 50 miles an hour, are they going to look like that? Or are they going to look like this? We're going to smash 2 more cars just to find out.
It's the final act of Carmageddon. 2 cars in a 50-mile-per-hour head-on collision.
Here's how this breaks down. At this end of the track, the yellow car.
And at this end sits the orange car.
And here in the middle, these 2 cars will meet in a 50-mile-per-hour handshake of destruction that will hopefully answer all the questions we have about the crash forces involved.
Adam's predicting those answers will give the thumbs up to Newton.
This one has really been a brain bender, but I have a prediction for this final experiment. I think that when all is said and done, it's going to prove that Jamie was wrong and that the fans were actually right. That when these 2 cars hit 50, they're going to look like the car that hit the wall at 50, not the one that hit the wall at 100.
And Jamie agrees.
Based on our small-scale testing, what we should see at the end of this head-on collision should look pretty much like the 50-mile-an-hour crash against a wall.
It's crunch time for a force impact. Will the full-scale test prove the fans right?
That's it. Well, I think it's time to do the final test. They're all set up.
It would seem so. I'm going to call it. Bring on the head-on collision.
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Both cars gain speed as they head headlong down the track towards their head-on collision. Then, as both cars reach 50 miles per hour,
It's about to happen.
the cables uncover.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle. And as the Mythbusters survey the wreck of a 2-car 50-mile-per-hour pileup, their planes spot the difference.
There's a windshield between them.
It's pretty evident, isn't it?
It really is.
It looks just like the 50-mile-an-hour against a wall crash.
And nothing like the 100.
Nope.
Amazing. This tells me the whole story. I didn't even see the accelerometer data or anything. These 2 cars, which hit each other at 50 miles an hour, look exactly like the car we smacked into the wall at 50 miles an hour. That tells me everything I need to know.
Well, the figures are in. The orange car got 52 G's. The yellow car got 58 G's, which, if you take a few G's, is the same as what we got against a wall at 50 miles an hour.
Gee whiz. And the damage data backs up those numbers. Both of the cars are virtually the same length as the 50-mile-per-hour wall test at 11.5 feet. And after a spectacular spree of automotive mayhem, there is irrefutable proof that those physicist fans had it right. Newton's third law, every action has an equal and opposite reaction, holds true. Although the two-car crash at 50 miles per hour doubles the speed, the energy of the crash is transferred to twice the mass, halving it, resulting in a crash that looks like just one car into a wall at 50 miles per hour.
I made a statement that two cars hitting each other at 50 miles an hour was the same as one car hitting a solid wall at 100. That was a mistake, but
That was a mistake. That was a mistake.
We don't get to hear the reason.
You want,
you know what? I'm okay with it. That's how you learn stuff.
was that a good reasoning?
No.
I'm
That
okay.
was a terrible reason.
All right.
I knew that was all TV. Like he totally knew that it would look like that.
So, all right. So when we see this type of question, what will do more damage? A car having head-on collision at 50 miles per hour, a car colliding into a wall at 50 miles per hour, or they will do the same? Well, they're going to do the same because the mass is doubled, right? So if we see a football example, all right, any football players, all right, so we don't have any football players in here, I don't think.
Oh, yeah, totally.
You know,
I enjoy football.
I enjoy football. I'd be down for some like rugby,
Like the pads are just like backyard.
just like backyard rugby. What?
Get yourself hurt.
All right, so if we look at one example, example number 12. So applying that information we just learned. Let's take a look at this. Okay? So number 12 says, hey, where's that at? Well, that's just silly. Huh. There it is. I was going to say. There we go. All right, so on a touchdown attempt, a 95-kilogram running back runs towards the end zone at 3.75 meters per second. A 111-kilogram linebacker, moving at 4.1 meters per second, meets the runner in a head-on collision. If the two players stick together, which direction do you think they're going to move? Before calculating, what direction do you think they're going to move? Left, right? All right, so the linebacker has a bigger mass and he's moving faster. All right, so we know they're going to move left. Now, what is their speed immediately after the collision? So this is where it gets a little tricky. All right, what is their speed? Okay, so what I'm going to do, I'm going to zoom in for a second. All right, so we know in a perfectly inelastic, we know that our momentum is going to be conserved. All right, our momentum is going to be conserved. So momentum initial is equal to my final momentum. So if you look at this, my momentum, I have two factors, right? The mass of player one and the velocity of player one. All right, and then I'm going to have to add on the mass of player two times the velocity of player two. Now that is actually going to equal, since they are stuck together, like the car example, we have to add the masses together. Okay, so mass of player one, mass of player two, and then that's going to be time. That's going to be this is what I'm solving for. Okay, so we should be able to plug in our numbers. All right, so the mass of player one was 95. The velocity of that guy was 3.75. Mass of player 2 was 111. This guy's velocity, ooh, negative, right? He's going the opposite direction. All right, so his velocity is negative 4.1. We're solving for VF. Okay? Two sig figs. Anybody got an answer? Negative what? Negative 0.48. So you guys get it? Negative 0.48. Perfect. Okay, meters per second. Negative 0.48. Okay, now the next question says, what is the initial and final kinetic energies? Okay, well, we have to apply our kinetic energy equation, so hopefully you guys kind of remember that. Yeah? What is it?
1/2 mass velocity squared.
Beautiful. Couldn't have said it better
I said it
myself.
on Monday and I'll say it again.
Kinetic energy. So my kinetic energy, so my initial, right? They're separated, right? They're separated. So I'm going to have 1/2 the mass of player 1, velocity of 1 squared, plus 1/2 mass of player 2, velocity of player 2 squared. So that's going to be my initial kinetic energy. My final kinetic energy, oh man, no, that looks all right. My final kinetic energy is 1/2 the mass of player 1 and 2 times my velocity, which I just calculated, squared. Okay, so try plugging all our numbers in here. 1/2 mass of player 1, velocity of player 1 squared. Did anybody get the kinetic energy initial? Maybe around 1600?
Yeah.
1600 joules?
That does not look right.
Yeah.
Doesn't look right.
I think it's right. You guys got 1600?
That's
Yeah.
I didn't square on this.
Why is it so large? How do we get to the final though?
Final. So you have half the mass of player 1. So mass of player 1 was 95. So you have 95 plus 111. And then you're going to take this velocity and square it. So you're going to have, I'm going to put it down here. You're going to have 1/2 95 plus 111 times negative 0.48 squared. So that's what you're going to plug in to find the final. And for the final, I got 2 sig figs, 23.
Yeah.
Yeah.
Maybe 27.
24.
22.7.
Yeah. 24. Okay. Meters per second. And that's how you would solve those. Or, oh my gosh, we're finding Wrong unit. Okay. How do we feel on that? Okay. Have you guys ever seen that hurts?
Oh, sports science love this.
Why? Okay. Why is it 1,600 joules? Like, why is it so large?
I would not.
Because you have two people coming together at, like, my force, your force.
Okay. Like, what would it power? Like, is there something you can give me in reference?
Would it be negative?
What would that power?
Oh yeah, like, I mean,
How long did the collision last? What was assumed?
1,600
Joules.
I don't know. I think it might be because I don't have a good grasp. Like, if you say 6'1", I know how tall that is, but I don't really know how powerful.
Here you go. There was 4.289.
Oh, okay. I get it now. Get it now.
Fair enough. All right, so we're gonna watch some sports science about guy who just won the Super Bowl. Two of them actually, just a different team.
Carrying around.
Our play of the week comes from New England's Rob Gronkowski, who's having a breakout year. He caught 2 TDs against the Redskins to give him 15 for the season, an NFL record for tight ends. But Gronkowski's best play of the game wasn't a touchdown. It was a short pass that he bulldozed into a 49-yard reception. On a 10-yard out, Tom Brady places the ball where only Gronkowski can reach it. But defender Dijon Gomes misses him by about 4 inches, and Gronk is back on his feet in less than half a second. Gomes pops up just as quickly and grabs him, but amazingly, this actually helps Gronk. Tackling is all about overcoming the ball carrier's momentum, which is a product of mass and velocity. Gronkowski is initially moving with a momentum of roughly 2,300 pound-feet per second. But when he starts dragging Gomes while he slows down, the extra 210 pounds of weight increases Gronk's overall momentum by an estimated 40%. If Reed Doughty had been able to hit Gronkowski alone, he might have driven him out of bounds. But he can't overcome Gronk's momentum because he essentially hits 2 players with a combined weight of 475 pounds. That's like running into one of the heaviest sumo wrestlers in the world. The impact changes Gronk's direction by only about 15 degrees, and Gronk drags both about 5 yards to the sideline. As he slips his would-be tacklers, he plants his right foot less than 5 inches from the sideline to stay on his feet. Josh Wilson is the next to get a shot, and his hit to the knee knocks Gronkowski's support outside his center of mass. But amazingly, Gronk remains upright long enough for his momentum to carry him another 13 yards, barreling his way to our play of the week. For ESPN Sports Science, I'm John Brinkus.
That did not look like 5 inches from the side. It looks like maybe.
it was just.
Well, he
I know,
said
I'm just
less
saying,
than
he's
5.
saying.
Sports on
Wait,
TV.
Rob
Gronkowski
Gronkowski, unstoppable.
It looks
runs. Let's
different.
watch that
It
one.
does. Say what?
Rob Gronkowski's unstoppable runs. Watch that.
That's not as good.
Let's watch
Watching
Aaron
Aaron
Rodgers.
Rodgers.
Aaron Rodgers is the GOAT.
Buddy, come on.
He's the MVP.
All right, it's 2 minutes. I got 2 minutes. We got 2 minutes.
Yeah.
He isn't as good as Tom Brady.
Shut up.
I'm sorry.
That's a bonus. Let's go.
All right, this is the last one though.
Rodgers
Last one.
I've been
back
there.
shoulder pass. It starts with arm strength. With his light and fast releases, timed at under 35 hundredths of a second, Aaron Rodgers can fire a 50-mile-per-hour bullet that arrives at a target 20 yards away in roughly 0.8 of a second. Next is timing. Rodgers launches his pass when his target is still about 7 yards from his break To time it perfectly, Rodgers must release the ball within a launch window lasting roughly 0.2 of a second, a margin of error literally faster than the blink of an eye. Next is precision. The back shoulder throw is often to a spot near the sideline, reducing the receiver's range and Rodgers' potential target size by more than 50%. To hit a small, precise target at 20 yards, Rodgers has a horizontal margin of error of less than 1.5 degrees. But the problem for defensive backs is that the human brain takes about 1/10 of a second to register information.
Excuse the interruption. Abby Trusty, would you come to the attendance office, please?
Sports Science Lab shows that even elite NFL DBs take an additional 0.4 of a second just to change directions. In that amount of time, the receiver can create more than 3 feet of separation, making a well-executed back shoulder pass virtually indefensible. What's scary is that Aaron Rodgers is just getting better. Since he took over the reins at Green Bay, his average yards per completion has increased by more than 10%, and his completion percentage has gone up 4 years in a row. For ESPN Sports Science, I'm John Perkins.
This was like 10 years ago, right?
Good
He's
grammar
not
and
getting better.
No, he's getting better every day.
Alright, so,
So then-
Now.
Holy cow, that was not used to.
wow,
Called it?
was it?
Yeah,
When what?
What'd you just say?
Alright,
I was only 9.
so, one last problem we're gonna look at, one last one. Alright, so we have a 0.007 kilogram bullet fired at 284 meters per second. Embeds itself in a block of mass that has 0.95 kilograms. That is attached to a ballistic pendulum. Okay. What is the velocity of the bullet and block after the inelastic collision? Okay. So in this one, make sure, I want you guys to get a good start on it. You guys know how to do it, right? Your initial momentum, is equal to your final momentum. Right? So mass mv1, m1v1 plus m2v2 is equal to the mass combined times the velocity. You're solving for the velocity final here. Okay. Solve for the velocity final.
Is that a large cell?
It's still at first. So yes, like the initial velocity of the block is 0. Double 07. That's pretty cool. Okay. So that's what it should look like when it's set up. Okay. For the velocity, 1 sig fig would take me to 2 meters per second. How do you guys do?
Zero.
Say that one more time. Let me think. So that's gonna be 0. What's these two combined? 1.988. 1.988 plus 0, so that would be 1. One divided, yeah. So when you add these two, that's where it gets tricky. So when you add them, you have to do the least amount of decimal places. Then B says, what kinetic energy does the block have after the inelastic collision? All right, so what's my kinetic energy equation? Okay, so in this case, 1/2 mass velocity squared. Now, 1/2, in this case, they're going to be stuck together, right? So my masses is combined, 0.007 plus 0.95. Velocity, I just solved. Q squared. Right?
I have a very random question.
I might have a random answer.
Okay. On the AP exam, how strict are they about the course?
That I don't know.
Okay.
And is it gonna be like an ABC?
I'm gonna find out. I'll find out for you.
Okay.
Yeah.
I just want to mentally prepare myself, just so like I can like review them before I go into the test, because I'm not ready.
Yep, I'll find out. Yep. You got an answer? What'd you get?
Well, I mean, if they're doing like sig figs, would we see something like when it's multiple choice, if it's 2.07 or like 2.06?
I don't think they're gonna be that mean to you.
Okay. I got 2 sig figs.
2 is the right answer. 2 joules. 2 joules.
Oh.
All right.
And then
Now,
6, 7.
C says, what is the max height? This is the last problem for today. What is the max height? So if we look at this problem, go back here. What is the max height? How can we get there? Anybody got a
I
guess?
have to calculate potential energy because that is the only equation that I know that has hydrogen.
You're exactly correct.
Holy
You're exactly correct. So when we analyze this, what is my potential energy equation?
Mass times gravity times height.
So that's my potential energy. So if you guys look at it, let's go back to our slides. If we look at this, right here, right after the bullet hits, we are full kinetic, right? Right after that bullet hits, we are 100% kinetic energy. Now, when we reach our full height, we're at 0% kinetic, which means we're at 100% potential. So essentially, this is going to equal that. Okay. So when you guys see this, right? When you see this, we have our mass times gravity times height. That is going to equal 1/2 the mass velocity squared. Okay. So when we combine, so we're going to have our mass is 0.007 plus 0.95 times gravity, 9.8, times h. I'm solving for h. That is equal to 1/2 the mass, 0.007 plus 0.95, times my velocity, which I just solved was 2. Well, 2 was up here. 2 squared. You guys want to simplify it? Do we like simplifying?
Yeah.
Let's get rid of the masses on both sides.
Yeah.
So 9.8 h is equal to 1/2 squared. So the height I got to be 0.2 meters.
Yeah, that's what I got.
Rock and roll. All right. How do we feel on inelastic equations?
Better today.
Inelastic feel pretty good. Front light's coming on 3, 2, 1. Back light's coming on 3, 2, 1. What? I gotta wake up. I was falling asleep.
Oh, okay. Yeah.
So now we only have 10 minutes left, so we can get a start on what we're gonna do. So what I did was, like I said, inelastic experiments are hard. You can look them up. Honestly, they're pretty interesting. But have a virtual, okay? Virtual lab, where this will take you through, all right, the objective, the procedure, all right? So there's a video that walks you through, it's pretty straightforward, all right? Very basic simulation. A little collision, okay? So you're gonna have to pause it. Collision. All right. Now, you're gonna have to record the time, the displacement. From that, we can calculate our momentum before and after. Okay? Sound good? We have 8 minutes, so I just want you guys to read over it. We will work on this tomorrow. All right, and we'll move on. This is not homework since I just introduced it to you guys. So just read over it. All right. If you guys want to get a start, you might want to start on table 1. Table 1 says displacement and time for a single cart that is moving. So what is the displacement for the single cart? So how far did it move after 1.07 seconds? How far did it move? All right. So try this out. If you guys have questions, let me know. Like I said, we will finish this tomorrow. Does that sound good, Brady? Sweet.
Oh, what was the answer to the riddle?
Wait.
It was a candle.